we have L and C, right? This for matching. In RF, right, there is this so-called a bad thing called as parasitics law. When you ask for a L, you may not just get an L. Along with it, you might get what is called as equivalent series resistor. So having just a pure good quality L of a certain nanohenry is going to be very difficult as the frequencies keep going up. You will have to have very smaller and smaller and smaller components. So in general, due to parasitics, if you ask L and C as a certain value, very precise value at a certain very high frequency application, it's going to be very challenging to realize them. So instead of using such discrete components, like component like L and C, what you can use is the so-called transmission line as a stub. We know that a transmission line has a certain impedance profile as depending on the length of the line. If you are terminating it with a certain load, how is it going to be? The input impedance is going to be. If you have a short-circuited line, if you have a certain length of the stub is nothing but a transmission line that is truncated with either an open circuit or a short circuit. So this is short circuit, and this is open circuit. So the length of the line is L stub. So the impedance that you see here, the Z in is going to be J Z naught tangent beta L stub. How do you know that? You know from the characteristic equation, right? The Z in is Z naught ZL plus J Z naught tangent beta L over Z naught plus J ZL tangent beta L. So if your ZL is 0, which is the case of a short circuit, then you will end up getting this. This means that if I have a L, the impedance that I get is J omega L. So for matching, if I require a certain reactance of J omega L, I need not have a discrete component L, but instead I can have a transmission line which has the same effect as J omega L, because even this input is J omega something. So as long as this omega L is the same as this term here, I can design the length of the stub so that this transmission line, a short circuited transmission line, behaves like an inductor. And that will be a very precise reactance without any parasitic effects. So that's the advantage of a stub over a discrete component. You can push the frequencies because you see the behavior is again J Z naught tangent beta L stub, where L stub is the length of the stub. The same with the open circuit stub. If you have a certain capacitance that you need, meaning that if you want a certain reactance of 1 over J omega C, which is actually negative J over omega C, this value that you want to have, this 1 over omega C, is exactly this value that you see here, that of an open circuited stub. I can choose the length of the stub so that this value is exactly the same as what you would get had it been a perfect discrete capacitor. So that is what is called a stub, and you can use them for impedance matching. And not only that, when you have this open circuited stub, which is Z naught cotangent beta L for an open circuited transmission line, if you were to represent it as a reactance, because it's only having an imaginary part, this Xn will be a negative number when L is less than lambda by 4. When Xn is negative, meaning it is capacitive. But the cotangent curves of periodic math, they are having both negative and positive, negative and positive. It is only negative up until lambda by 4. But beyond lambda by 4 to lambda by 2, it shoots up to the positive. That means Xn is going to be greater than 0 means it's an inductor. So the same open circuited stub, I can design with an additional length, then I can even realize an inductor for that matter. So be it a capacitor or be it an inductor, I can either realize using an open circuited or a short circuited stub. I can always change the length. If the length is changed by lambda by 4, the load that you have appears as if it's inverted, right? Reciprocal, right? So making capacitive and inductive by adjusting by additional lambda by 4 length is very easy. So I can use open circuited stub to do that. The same concept can be used for a short circuited stub where if you were to say this whole thing has to be my reactance, my tangent beta L is going to be positive until L is less than lambda by 4. My Xn is greater than 0, which means it's inductive. But in this region, my Xn is going to be less than 0, which means it is capacitive. So the same short circuited stub, depending on the length of the line, can either be used to realize as if it is an inductor or as if it is a capacitor. That means either its reactance is positive or its reactance is negative.